The old joke is that chemists have solutions. And while we have solutions to many things, we also work with solutions. Turns out that solutions are pretty important for us to begin to understand. They're everywhere. You're a solution, in fact. Kind of, you can think of it as you're a big sack containing other little sacks that we call cells that are made up of solutions. So all those biochemical reactions that take place in your cells, well, they're all taking place in solutions. In fact, we're swimming in a solution. The air around us is a solution. Your book goes on to say that Earth is widely referred to as the water planet. Life exists here because liquid water is abundant. Debate over the existence of life elsewhere in the universe hinges on the prospect that liquid water exists on other planets. So this hydrosphere, the fact that Earth is a water planet and surrounded by solutions, so very many chemical processes and changes that take place here on Earth happen in solutions. So it's important for us to understand what these things are. So let's write some definitions down. So first off, solution. So a solution is just any homogeneous mixture. So let's review what these two terms mean, homogeneous and mixture. Remember, mixture is anything that has variable composition. So that's the key component of being a mixture. So variable composition. So that means we can change what it's made up of. Homogeneous just means uniform. So a homogeneous mixture will be the same when you look in one part of it as you look in another, and there will be no boundaries separating one region from another. So a solution is just any homogeneous mixture. So examples of solutions, Kool-Aid, right, is a homogeneous liquid mixture. Seawater, if you omit all the little fish and life forms that might be swimming around in it. So seawater. Brass. Now brass is a solid. You may not think of it as being a solution, but it in fact is a homogeneous mixture of two metals, copper and zinc. Air is another example of a homogeneous mixture. Again, you may not think of it as being a solution, but it is. It's a mixture of different things that can have variable composition, right? Some days it's kind of humid out, so there's a lot of water vapor in the air. Some days it's very dry, so there's less water vapor in the air. The carbon dioxide amounts change with the seasons and between day and night because of plants doing their thing. So that's a solution. So we can break a solution up into two parts. There's the solvent, and chemists think of the solvent as the major component. So whatever you have most of, that is called your solvent, major component. Everything else is a solute. You got to keep track of your solvents and your solutes. So the solvent is the thing that does the dissolving, and the solute is the thing that gets dissolved. The solute is any minor component. Just write dash dash right there to say component. So the solute is any minor component, and it's the stuff that gets dissolved. So in air, for example, air is made up of about 3/4 nitrogen into gas, about 20% oxygen, and a little bit, 1% or so, of argon. So in this case, nitrogen would be the solvent. We could think of oxygen and argon as being solutes in that solvent. Now, typically, we think about solutions as being liquid solutions. And this chapter, and seawater and cells, all involve aqueous solutions. So that's going to be something that we're going to want to highlight here, aqueous solutions. And an aqueous solution just means that water is the solvent. Water is a very powerful solvent, in fact. It's sometimes called the universal solvent, and we see a lot of it. So let's think a little bit about how a solution happened. Here's an example right here of making a solution. So what we've got here is a spoonful of sugar. Helps the medicine go down, according to Mary Poppins, right? So maybe it'll help chemistry go down too. So we have this sugar, and we're going to dissolve it into this water. So we're going to try to dissolve sugar into water, right? And we do that when we add sugar to our iced tea or our coffee. So if we have a microscopic view, these sugar crystals are made up of a nice orderly arrangement of sugar molecules. Now most table sugar, the principal component is sucrose, And this is a sucrose molecule. It's a fairly complicated molecule. It's made of carbon, the darker atoms, oxygen, the red atoms, and hydrogen, the little white atoms represented here. But because it's so complicated, we're just going to represent them as little red spheres here in our picture. So in our picture, what we have going on here, let's scroll up a little bit. We're going to add this to the water. Here's our microscopic viewpoint of water. Let me scroll down a little bit so you can see that. So here are little water molecules. So, there's a water molecule right there. So it's made up of two hydrogens. So there's a hydrogen, that little blue bit right there. Here's another hydrogen, that little blue bit right there. And there's an oxygen, the red atom. So those three atoms together make this little V-shaped molecule, H2O. Chemists might draw it like this, showing that there are covalent bonds here between the hydrogens and the oxygens. So these water molecules are all dancing around, bumping in here, tumbling around on each other in constant motion inside this liquid. Now what we're going to do is we're going to take that spoonful of sugar and dissolve it. So what happens in the beaker, of course, after we stir for a little while, is that the pile of sugar at the bottom goes away, and we end up with a clear solution that looks a lot like water. But at the microscopic level, here's what we would see. That sugar crystal, remember up here, these little crystals of sugar where we had our nice orderly arrangement of sucrose molecules, they have broken up, boom, and they are now all over the place, surrounded by these water molecules. So these water molecules now make a little shell around these sucrose molecules and interact with them and cause them to separate. And so that process is dissolution at the molecular level. So we've made a sugar-water solution here by breaking up that sugar crystal and solving these guys. Now again, this is a variable mixture because we can add different amounts of the sugar. We can make this sweeter and sweeter and sweeter up to a point. Now at some point you're going to get so many of these sugar molecules in here that the water simply can't accept anymore. That point is what we call saturation. Saturation occurs when no more solute will dissolve in a given amount of solvent. So when no more solute will dissolve in a given amount of solvent, you have reached saturation. And at that point, the sugar is just going to pile up at the bottom, and no matter how we stir, it's not going to dissolve. Now, we might get sneaky and go in and heat it up. So if you heat it up, you can get more to dissolve. So saturation is a property that depends upon the temperature of the solution. So that's how we make a solution. So we could talk about a solution as being concentrated, if, say, we are close to saturation, or if we just added a few crystals of sugar to this, then it might be very dilute. So these are two rough terms that we might use to describe a solution. But solutions are variable. They can be anywhere in between this, and we as scientists want to come up with more specific ways of describing the composition of this solution, how it is made up. And so we develop ways of talking about concentration. So let's scroll down a little bit and talk about concentration. So concentration is just a way of expressing with a quantity, a measured value, the amount of stuff, the variable composition of our solution. And almost always, concentration will be expressed this way. So concentration tells us about the ratio of the part to the whole. So we need to know something about the amount of a given solute that is dissolved in a certain amount of solution. Or as an alternative, we can think about the amount of solute, so I'll just abbreviate that AMT, amount of solute, in a given amount of solvent. So either way, so we need to talk about a part to a whole. So the minor component to either the whole thing or the major component. Either one of these could be good definitions of concentration. So both of these numbers then, if this is a ratio of part to whole, is going to be a fraction, right? Because we don't have the whole thing up here in the numerator. So this is going to be a fraction. So typically we will express concentration in percentages. This is one way that we could express the concentration as percent. Now to be a percentage, we need to make sure that our units cancel out. So typically we will talk about either a weight percent, so I'll abbreviate that WT, which is going to be the mass of the solute divided by the total mass of the solution. So I'll abbreviate SOLN is my abbreviation for solution. And then to make that a percentage, we multiply this by 100. So for example, if you dissolve 10 grams of sugar in 100 total grams of solution, so that solution will include both the sugar and the water. So let's just do that real quickly. So we've got 10 grams of sugar, sucrose, in 100 grams of total solution. And now what's important to realize here is that this 100 grams of solution right here is made up of 10 grams of sucrose. I'll abbreviate that SUC, sorry about that. Anyway, 10 grams of sugar, all right. 10 grams of sucrose plus 90 grams water to make up 100 grams of solution. So mass is conserved, we can just add those together. And then we would just multiply by 100 to convert this into a percentage. And so this would be a 10% solution. So a 10% sucrose solution. And now we have a very specific number that tells us about the composition of that solution. So I told you that we could measure this as a weight percentage. We can also measure it as a volume percent. So percent by volume. Same way, we would just figure out the volume of our solute that we added divided by the volume of solution. And again, we multiply that by 100 so that it's a percentage. It's a ratio of a part to a whole. And so these would both need to be in volume units, milliliters or liters or gallons or whatever. So for example, we do this often when we've got one liquid dissolving in another liquid. So for example, ethanol, we could dissolve that in water. So ethanol is an alcohol. The OL ending tells you it's an alcohol, and it's the alcohol that is in grain alcohol. So this is the stuff that you can consume. And so sometimes if you've ever looked at a bottle of grain alcohol, they will talk about the proof. So they may say that it is 100 proof. So 100 proof is just half of the, if you take the proof and divide that by 2, so proof divided by 2 gives you the volume percent of alcohol. That's volume percent. So 180 proof would be 90% by volume ethanol. So what you do is you just measure out the amount of volume of ethanol that you'd have and then divide that by the total volume of solution. I'll give you one warning here. There's a very interesting chemical fact that for very many things that you dissolve, it is the case that 10 milliliters of ethanol plus 90 milliliters of water does not quite equal 100 milliliters of total solution. Funny thing about molecules, when you start mixing them together, sometimes they change the amount of space between the molecules, and that can actually change their volumes. So while masses are additive, we can add them together and get the total, we can't always do that with volumes. So generally you can't do that. Now we will often use this as an approximation because it's approximately true, and certainly when you're adding tiny amounts of solute to a lot of water, it's not going to be a big change. So we will oftentimes assume that volumes are additive. Anyway, so that's volume percent. Oftentimes we will see really tiny amounts of stuff dissolved in a solution. And so for those purposes, we have some other units that we use, ppm and ppb, which stand for parts per million and parts per billion respectively. So ppm for parts per million, ppb for parts per billion. So one way to think of a percentage is it's really just a part per 100. So 20% means that 20 parts of every 100 things that you have are the solute. So ppm and ppb then are the parts per million and parts per billion instead of parts per 100. And we would calculate these just like we did with percentages. So we would take, for example, the mass of solute, divide that by the mass of solution, and in this case, we've got a really tiny amount of solution. So the fraction that of solute. So the tiny amount of solute, so micrograms, let's say, or nanograms, something really small. So the fraction that we get here is going to be really tiny. So to make it bigger, what we're going to do is instead of multiplying by 100, we're going to multiply by a bigger number. In this case, a million. So it's parts per million. We're going to multiply by 10 to the power 6, which is a million. So that would be parts per million. parts per billion, ppb, would be equal to the same thing, mass of the solute divided by the mass of the solution times, in this case, a billion, which is 10 raised to the power 9. So those are the definitions for parts per million and parts per billion. So let's work a quick little example problem using parts per million and parts per billion. Okay, so here's a problem. This comes from your textbook, so we'll work through this. It says the average concentration of chloride in seawater is 19.353 grams of chloride per kilogram of seawater. So the World Health Organization says that safe drinking water should not have more than 250 parts per million chloride. So if you get too much sodium and too much chloride in your drinking water, what happens is it starts to suck water out of your cells because your body is trying to dilute that seawater, and you end up actually dehydrating by drinking seawater. It's very dangerous. So how much more concentrated is seawater? So we're trying to compare 250 ppm to 19.353 grams of chloride per kilogram. So we got a problem here because we can't directly compare them because they are in different units. So we need to convert them so that they are in the same units. So what we're going to do is convert this top number so that it is in ppm. So what we need to do is figure out the mass of chloride. We can do that in grams. And then we need to divide by the mass of solution in grams. So both these units need to be the same. And we're going to convert it to ppm. So finally we're going to multiply by 10 to the 6. So I'm just using my definition for ppm here to figure out what I need to do. Okay, so do I know the mass of chloride? What I know up here is 19.353 grams of chloride per, or out of, every 1 kilogram of solution. So I can use those two numbers here in this equation. So the mass of chloride is going to be 19.353 grams chloride. Just go ahead and keep the labels in there. And the mass of solution. Now we have to be careful, we want both in the same units. So kilograms, so that's going to be per, and there's no number here, but I'm going to infer that that is 1 kilogram. So 1 kilogram is the same as 1,000 grams. So here's 1,000 grams of seawater. And now what we're going to do is multiply that by 10 to the 6th. So we punch this into our calculator, and we get 19,353 parts per million chloride. So wow, that's way bigger than 250. How much bigger? Let's see if we can calculate that out, because that's really what the question asked us. How much more concentrated? So whenever a question is asking for how much more, you want to give a number that you would have to multiply or divide by to get that number. So how much more? 19,353. How many times does 250 go into that? That would tell us how much bigger this number is than this one. So when you divide those out, you get a number that is, to three significant figures, 77.4. So 77 times bigger than the safe drinking limit. So don't drink a lot of seawater, okay? If you drink a little bit, not going to kill you, but you don't want to keep on doing that because for regular drinking water, because you will dehydrate. Now we turn to another concentration unit, and this one is probably more common in chemistry. It's called molarity. So molarity is a very important concentration unit because it lets chemists count molecules by volume. We can go in and we can count the number of dissolved molecules by measuring volume. Now you recall that when we're thinking about chemical reactions, that everything is in terms of atoms and molecules. Everything is at that level. And so we want to be able to do that with a solution. So imagine that we've got some stuff that we're trying to dissolve, right? So here's some particles, some solid. Here's some of the molecules that make up that solid. Maybe it's a crystal, and so they're stacked and organized in a nice little array. What we're going to do is add those to a beaker of water. I'm not going to draw in the water molecules, but we're going to know that they're there. So what happens is, again, these particles are going to break up. So there they are, all floating around now, surrounded by water molecules in this solution. And so what we'd like to be able to do is count the number of particles that are in this whole solution. Now, of course, if this were a real crystal that we could see with our eyes, there would be lots of particles in here. So we're going to do what chemists normally do and count them in groups, and we use that special group of a mole. Just like we could group things in pairs or dozens, we chemists group things in moles because it's a big collection of things. So we want to count how many moles, just like how many dozens, how many moles of particles are floating around in this solution. And so that's our definition of molarity. Now it still follows that concentration unit that I talked to you about before, that concentration is always a ratio of the part, the amount of solute, divided by some number that either tells us about the amount of solution or the amount of solvent. Okay, so there's our basic definition for concentration. So then molarity, we want to count particles. So molarity is given the symbol capital M, so capital M for molarity, and it is defined this way. So we're going to measure the amount of solute by counting the particles. So we want to know the moles of solute. And then the amount of solution we're going to represent by volume, and most commonly in a lab setting we'll use volume in liters. So this is going to be liters of total solution. Right, so I underlined total here, my abbreviation for total, tote. I abbreviated total because this is not just the volume of the solvent. It is the volume of the solute plus the solvent when they're both mixed together to make the total solution. So this is our definition for molarity. So we're counting moles per liter. So there are a couple of important things that you can do with molarity. So let's look at some examples. So for example, if we know that, say, we have a 0.10 molar, so we use M as our unit, and we say molar, kind of like the tooth. So we say molar, 0.1 molar solution of sodium chloride. I'm going to write AQ next to the sodium chloride. That lets us know that it's dissolved in water. So we've got a solution that has that concentration. So what is this telling us? This is telling us that there are 0.10 moles of sodium chloride formula units dissolved in 1 liter of solution. SOLN, my abbreviation there. So that's what the molarity unit means. So we can use this as a way of calculating the number of particles if we get a certain volume. So let's say we take 25 milliliters of the solution, and what I want to know is how many moles of NaCl is that? So we've taken a certain volume of this whole solution, so we're going to get a certain number of these particles, right? If I just kind of go in here to my drawing and I scoop out that number of particles right there, so I scoop that out, right? So I've gotten a certain volume, and I want to know, well, how many moles of particles are in there? I want to go in and count those. So we're going to try to do that in this problem. So we've got milliliters right here, and we would like to convert that into moles. So you'll notice that right here I can use molarity, which is moles divided by liters, as though it were a conversion factor. So what I'm going to do first is take my 25 milliliters, and I notice that this conversion factor, this ratio of moles to liters, has liters as the volume unit, and I've got milliliters here, so I should convert that first. So I need to convert from milliliters into liters, so liters goes upstairs and milliliters downstairs to cancel out. And then I need some numbers that will help me think about, well, how many liters in a milliliter, or how many milliliters in a liter. So I remember that there are 1,000 milliliters in 1 liter. Or you could remember that there are 10 to the negative third liters in 1 milliliter. That works too. So milliliters cancel out. Now we are ready to use this conversion factor to figure out how many moles of HCl we have. So we've got 0.1 moles of NaCl, I said HCl, but NaCl, sodium chloride, in every 1 liter of solution. And we've taken 25 milliliters of that solution. So liters are going to cancel out, and when we're done, we'll know how many moles, like we've counted these particles. We've counted them in these groups, so we'll know how many moles we have. So we're going to quickly punch that into our calculator, and we get to two significant figures, 2.5 times 10 to the negative 3 moles NaCl. So that's how we've counted number of moles in a certain molarity solution. So now we want to know, how do you calculate the molarity of a solution? So suppose we go out and we take 3 grams of NaCl. We're going to take those 3 grams of NaCl, we're going to add them into a very special piece of glassware that you have in chemistry labs called a volumetric flask. So volumetric flask is a precision piece of glassware that's designed to contain a fixed volume. And it has etched around the neck a thin little line that's cut into the glass all the way around the neck of the flask. And when you fill the water up to that mark, it's designed to contain whatever volume it says. So in this case, let's imagine that our flask is a 500 milliliter volumetric flask. So I put 3 grams of sodium chloride in there, so the 3 grams goes in the bottom. And then I fill it up to the mark with water, so our meniscus ends up sitting right on top of that little mark. And we dissolve it all, so the sodium chloride dissolves. And I want to know, well, what is the molarity of this solution? Okay, so to figure that out, let's go back to our definition of molarity. So I need number of moles of solute. So what is my solute? Well, I'm adding sodium chloride, that's the minor component. I've got lots of water, so that's our major component. So the solute is NaCl. So I need to figure out how many moles of NaCl I have. Then I'm going to divide this by the total liters of solution. So notice here that this 500 milliliters, that's going to be the total volume in here. That's not how much water I'm adding. I'm adding up to the mark. So there's going to be volume due to the water plus the little volume that the sodium chloride down here is taking up. So now I need to calculate this. So what do I know? Do I know moles? No, I do not know moles. So that's something I'm going to have to figure out to work this problem. What about liters? Do I know total liters of solution? When I mix this up, I know I will have 500 milliliters. So I do know something about volume. I know that it's 500 milliliters. So I don't exactly know liters, but I do know milliliters. So presumably from those two pieces of information, I can figure things out. So how will I find this moles of NaCl? Well, those of you that are remembering your previous chapter, we know we have 3 grams of NaCl, and we know that we can go from grams to moles using molar mass as a conversion factor. So we will need to calculate the molar mass of sodium chloride, and then we can convert to grams to moles. So even though I don't know what this is, I can figure it out, and that makes me happy. So we'll be able to punch into this equation as soon as we get these numbers. So the first thing to do is to start your calculation, NaCl, and now we need to convert first into moles. So we're going to get our moles here, and we're going to get rid of our gram unit, so that goes downstairs. Grams of NaCl will cancel out. We want moles of NaCl. And so this is telling you that you're going to be dividing by the molar mass, because molar mass is grams out of moles, or grams per mole. So we need to go to the periodic table and add these up. So the periodic table will tell you that sodium has a mass of 22.989768 grams per mole, and that chlorine is 35.4527 grams per mole, which gives you a total of 47.295 grams per every 1 mole. So what we're going to do is take 3 divided by this number, and that will give us our number of moles, and that is 6.34 times 10 to the negative 2 moles. So now we know moles. Yay, so we're happy. So now we just need to plug into our molarity equation. So our molarity is going to be 6.34 times 10 to the negative 2 moles of NaCl. That's our solute. We need to divide by the total volume of solution. So we have 500 milliliters up here, 500 milliliters. So 500 milliliters is 0.500 liters. So we know that there are 1,000 milliliters in 1 liter, so we just move our decimal place over by 3, and because we're dividing by 1,000, and that will convert our number into liters. So there we have our unit, moles per liter, and that's the molarity unit. So we just need to divide this number by 0.5, and you'll get 0.126, so we're going to round that to 0.13 molar. So this solution that we just mixed up is a 0.13 molar solution.